Now we're going to do an example. A small plastic ball having mass 2 grams and electric charge +1 microcoulombs moves in the vicinity of a stationary metal ball with a charge of +2 microcoulombs. When the plastic ball is 0.1 meters from the metal one, it is moving directly away from it with a speed of 5 meters per second. So the question, two questions. A, what is the speed when the two balls are 0.2 meters apart? And B, how would the situation change if the plastic ball had a charge of -0.1 microcoulombs? So we're just going to go through the solution. Because of the conservative nature of force, total mechanical energy, kinetic, plus potential is conserved. First, we list all initial and final kinetic and potential energies, K1, K2, U1 and U2 respectively. So the initial kinetic energy is going to be the half mass times velocity squared. That's the equation for kinetic energy. And the mass is 2 grams, so we're going to write this in the proper SI units. 2 times 10 to the minus 3 kilograms. And the velocity is 5 meters per second, so we just square that. And we start, the initial kinetic energy is 0.025 joules, so we got that. The final kinetic energy, we're given that all we have here is the mass. We don't know what the final velocity, because that's what we're after finding. So we just write down a half, 2 times 10 to the minus 3 here, and we just write down V2 to V2 squared. And the initial potential energy is 1 over 4 pi epsilon naught. That gives us this number. And then we've got Q1, Q2, well, we're given both of those, so we can plug those in, which is 0.1 microcoulombs and 2 microcoulombs over the distance. We're given the initial distance is 0.1, so we can write down the initial potential energy is 0.018 joules. We can also work out the final potential energy, because we've got the value of both the charges, and we're given that the final distance is 0.2 meters apart, so we can work out the final potential energy is 4 pi over epsilon naught, which is 8.99 10 to the 9, and then again we've got the 0.1 10 to the minus 6 coulombs, so 0.1 coulombs, microcoulombs, and 2 microcoulombs divided by 0.2 meters gives us 0.009 joules. So we've got everything now. So we know from the conservation of energy, the initial kinetic energy plus the initial potential is going to be equal to the final kinetic energy plus the final potential. So we just plug all those in. The only one we've got here that is unknown is V2. So we'll plug all these in and then simply rearrange for V2, and we get V2 equals 5.83 meters per second. So we can see the speed has increased away from the metal ball, so we know that the force is pushing it away, it's repulsive. So that's the answer for point A. Now for question B, if the moving charge is negative, the force on it is attractive rather than repulsive, and we expect the final speed to slow down rather than speed up. The only difference in the calculation above is that the potential energy quantities are negative, so we can write this whole thing down again, but we can just change the potential energy to negative parts, and then we plug it all in again, and we'll find the unknown V2 again to be 4 meters per second. So that's the answer. So that's an example of conservation, the conservation of energy. So we got initial energy, and it's going to be equal to the final energy. Right, so here's a final point about how we can treat electric potential energy. The work moving from A to B is the potential energy UA minus the potential energy UB. Now, when the potential energy at A is greater than the potential energy at B, this work is positive. The field and the potential energy decreases during the displacement. In this case, the field does positive work on the particle, as the particle falls from a point of higher potential energy to a point of lower potential energy. So this is the main point of this whole discussion